JTAG and Android kernel debugging. My name is Mike Anderson. I am Chief Scientist and Chief Technology Officer for the PTR Group. We've been working with Android now for about 4 years. Been working with embedded Linux since about 1999, so been working with the Linux side of it for quite some time. What we're going to be focusing on here in this tutorial is the process of using a JTAG to do Android kernel debugging. Now, we have a lot of things going for us here. In the first part, one of the major things we have going for us is that this is, in fact, the Linux kernel. So with the Linux kernel in place, there are going to be a lot of things that we can take advantage of in terms of debugging interfaces and techniques so that we don't have to reinvent the wheel here. We'll be talking a little bit about device drivers in Android, how they come into the kernel, how they're built, what they look like, the types of interfaces that they have. This is not, unfortunately, a class on Android device drivers, but unfortunately, we do have to have a little bit of understanding and background on Android device drivers in order to understand how the JTAG works. We'll look at the JTAG interface and the types of JTAG interfaces that we have at our disposal. Then we'll see how the JTAG is used to debug the kernel. Now, there are going to be several very key transitions that we'll talk about with respect to the kernel. These are usually transitions coming out of the flash, going into the initial load of the kernel, and then when the kernel transitions from physical address space to virtual address space. So all of those are very key transitions that the JTAG is really the only mechanism that we have access to that will allow us to trap and step through those particular transitions. We'll then move into the OpenOCD project. Now, OpenOCD is not obsessive compulsive disorder. It is the on-chip debug. And the OpenOCD project has been around for a while. We'll talk a little bit about where it came from and what its goals are. But we're primarily focused on, okay, now how do we take advantage of open software like OpenOCD to be able to debug inside of the kernel? Then we'll look at how you go about getting and installing OpenOCD. And I happen to be running, this is all very fresh information because I'm running the latest Git version of OpenOCD as it was last night. So hopefully, made my sacrifices to the demo gods this morning. Hopefully it will work at some level. It is version 0.6.0 of OpenOCD. So that version has not been officially released yet. The reason that I went with that version is because there are some instability problems with the BeagleBoard XM that I happen to be using. So OpenOCD works great for less bleeding edge processors, but when you start talking about the Panda and the Cortex A9 processor and some issues with the DM37 series, the DaVinci series on TI, there are a few little quirks about OpenOCD that we'll talk about as we go through. We'll talk about how you start OpenOCD and then how you connect to it with GDB. Of course, the whole purpose here is to talk about debugging kernel code. So we'll show you exactly what you have to do on the Android side in order to be able to get the addresses that you need to have to load into GDB so that you can then load the driver's address space and be able to actually start doing some debugging. So lots of things have to happen, and this, as you notice, this is a 2-session tutorial. So somewhere in the middle, if someone would just keep an eye on break time. I think it's, 11:45 is the break. So we'll try to make sure that we actually get a break. But as I'm going through this thing, I tend to be time-wise. So please. All right. So thanks to the fact that we're using the Linux kernel, Android has access to several different device driver types. The primary device driver that will be is the character driver. Now, the character driver in Android, normally in Linux, character drivers are about 80% of all of the drivers. In Android, they're more like 85 to 90% of all the drivers. because it turns out that the GPIOs, a lot of I2C interfaces, the touch screen, all those sorts of things inside of Android devices all come in as character interfaces. Block interfaces are file systems. So we will, in fact, have file system support for things like our typical Flash interface, drivers for different types of file systems. All those sorts of things we will have to deal with. But fortunately, those tend to be in the minority. And then, of course, probably the more prevalent between block and network drivers are the network drivers. The network drivers in Android are a bit of voodoo, is perhaps a kind thing to say about network drivers. Because network drivers actually come in from the BSD 4.4 operating system, their interface into the kernel is a little bit different than what we see with block and character drivers. So we'll talk a little bit more about that as we get a little further into the presentation. Now, because of the normal driver model, and what I mean by that is we have the ability to load a driver up standard open-close read-write interface type of. Now, this changes because what it does is it then allows the Android user space to write into the HAL, have its HAL, and present that information down to. But as a developer, responsible for making sure the connection into the HAL. What we have to do as driver writers need to face it the approach, whether that's the sensor HAL, the audio HAL, the video HAL, any of those types of interfaces. From kernel space that those applications are expecting. Now, it's also possible to have user mode drivers. And of course, in Android, more so than we see in Linux, there's more of a push for user mode drivers in Android, simply because user mode drivers are easier to debug than kernel mode drivers. Now, in order to really debug a user mode driver, we need to think in terms of what is it trying to do. If the driver is simply a USB interface, then we can talk to Android's equivalent of libUSB and communicate that way. Of course, USB has this whole plug-in. It identifies itself. You get a vendor ID and a product ID, and then you try to figure out what it is. All that sort of business happening. And much of that can be done in user space. But when we talk about buttons and screens and audio and things of that sort, that tends to be more of something that we see in kernel space rather than in user space. That being said, we can't always get access to registers. /dev/mem does exist in Android. We can open it up and mmap it and then get access to registers if we choose to do that. That's kind of a dangerous thing to do, but in many cases when I'm presented with a new piece of hardware, they'll say, oh yeah, the hardware's working. Well, what does it mean to a hardware guy when he says the hardware works? It means that he's plugged it in and the magic blue smoke has not escaped. As a consequence, he will say something is working when the chip is actually wired up backwards because it didn't smoke. He took the layout for the chip, he got the footprint if it was on the bottom of the board, he put it on the top of the board, now the chip's backwards. It doesn't smoke, but it doesn't work either. So having access to the mem, I actually have a set of functions that are called peek and poke, for all of you old basic folks, that allow me to reach out and touch registers from user space. And those applications then allow me to tickle the various registers and make sure we can light something up before we even bother to try and go out and do some work with it. I did have one case where they were trying to drive a GPIO. It was a board that supposedly worked. It was out there. They had already experimented with it. They wanted to add a new feature. So they wanted to turn on a GPIO on the main processor. And I'm sitting there with the board. I turn on the GPIO and drive it, and the CPU goes, explodes. And I go, software's not supposed to do that. So I went to the hardware designer and said, it blowed up. He goes, no. The driver. And I want to have never gone through the Android build process, and we haven't had an opportunity to experiment with the build process, just simply saying, oh, you need to have debug. You may have to rebuild the entire function. platform and how. This Beagle board does is it goes out and downloads all of its file system from NFS. So it does, in fact, load the kernel off the SD card, but everything else is. Very bad thing. Friends at the TS. The excuse me, ARM, this is typically going to be U-boot. A port of Android running on the x86 since the 2.1 days, but now we have official Google support for the C code that runs in the Linux kernel. And this is .text. And in that devices that user this particular loadable module. There we go. going to be dynamically loaded. At 11:45. The new interface allows you to attach a much more object-oriented interface. There's a lot of reasons why you might use it. That you no. Probably 70%, 80% still use the register called. It's changing a little bit. Push you to the new. The drive with kernel.
Everybody has to do that. I'm noticing this is your video recording.
Yeah.
The audio seems to be bad because it's staying down below in the blue most
Okay.
of the time during talk.
Well, then that means that those people that didn't come will just miss out. I'm sorry. I don't know. I'm not sure exactly.
You're not running it yourself.
No, I'm not running it. That's not mine. I have my mic. Check one. Yeah, that's working. So
Okay. Cool.
I assume that whoever's running it will figure it out.
Thanks, Mike.
Yep.
Good question. What's the email address?
It's on the front of the presentation. It's mike@theptrgroup.com.
I would like to get a method how to connect to UI of.
That's me.
Oh, great.
So
So,
be happy to send it to you.
and in the beginning of presentation, I mentioned what driver have to be built as a loadable module in order to debug it.
It doesn't have to be built as a loadable module. It's just a lot easier to debug it if it's built as a loadable module. If it's built as a statically linked module, then what will happen is typically during the boot cycle, it will panic and the whole thing will lock up. So being able to debug it at that point, you really don't have any infrastructure in place. You might even have the kernel die before the serial port starts working, in which case it looks like uncompressing kernel ... dead. And there's actually a lot of stuff out there, just that we hadn't been able to initialize the serial driver to actually print any of it out. The JTAG can help you there, and I'll show you how to use the JTAG to dump the print buffers.
The best thing is you can load and upload modules without
That's key. Just being able to load and unload the module. You load it, okay, it didn't work, unload it, try it again. Yeah, but doing a statically linked driver, yes, you can debug a statically linked driver, but it is so much harder.
because in case you work with driver, which is part of the boot process, for example, some storage driver.
Yeah, if it's a storage driver, then you really don't have much choice in that case. You're going to have to. Well, you could load it from an initRD, and in the initRD, you could dynamically load it. So it can still be a dynamically loaded module, but but if you have to statically link it, it's just going to be that much more difficult. Impossible, just a nuisance.
I'm going to be the bad guy and get in there now. If you want to keep asking questions, that's cool, but can we move it out?
Oh, sure.
So the next guy can come in.
No, I am the next guy.
In that case, ignore me. I should have double checked the list, shouldn't I?
Yeah.
Here we go. Sorry?
Are you running the?
I know, I'm not.
Oh, just send me an email, and I'll be happy to send it to you. I'll send you the code. I mean, we pulled it off the web, so I don't know.
You turning on or not?
Yeah, I assume it's on. Green light.
We are.
There's
We
a
are.
buzz on the speaker.
Okay. The speakers are not ours.
I'm just going to complain.
Yeah.
Chuck, no, I will complain. We're not doing. I'm in charge of.
Statically linked or dynamically loaded?
What do you suggest?
I would suggest dynamically loaded because if you can. I mean, obviously, if it's the console, then it makes it difficult to dynamically load it.
Yeah, console.
If it's the console output, then you really have to go at it as a statically linked module because that's one of the first drivers that gets initialized. In which case, then you really do end up having to use the JTAG to be able to step through, or KGDB, but KGDB, yeah, requires a serial port. So
Do you use the KGDB stub? Do you use the KGDB stub in conjunction with your stuff, or no? Is it separate?
no, well, as long as you've got the kernel compiled for debugging, then you don't need the KGDB stuff. And that makes the kernel a little bit smaller, a little bit easier to manage. But as a general rule, I will turn the KGDB stuff on just simply because I don't always have my JTAG sitting next to me. And sometimes I just need to talk to it through the serial port.
Talk with you how the symbol, sensitive to the symbols and the load.
Oh, yeah. Yeah, we'll show you an example. Yeah, we'll show you an example of all that in the second session.
I'm
Right.
up to the toolchain working group inside the
Okay.
Yep. Sorry, I'm not sure if I'm going to be here for the second half. Are you using GDB, OpenOCD?
OpenOCD.
Right.
Yeah, with GDB.
We've been considering doing some work on it where we do things skill-based, and the guy I had lined up isn't going to do anything, so it isn't available, but I'm interested in talking later.
Oh, sure.
Well, what do you think should be improved?
Yeah.
Also, there's, thanks,
Me.
I don't have the card on me, but I'll
Okay.
write down later. We've also been talking with ST. Apparently they have a GDB kernel target. So just like you can debug threads and dynamically loaded things under user space, do the same in the kernel.
Right.
So you loads a model.
Yeah, it runs in run mode as well as debug mode. So with JTAGs, you have two different modes that the JTAG can run in on the ARM. It can run in debug mode, which is stop mode, which is what you'd use for debugging the kernel, or you can run in run mode, which says you're debugging user space applications and the kernel is still running. So
This is, so when you load a module, how do you resolve the symbols in it?
we'll talk about that.
So they have a patch that happens automatically.
Oh, okay.
And
Well,
also, so you can borrow it into the kernel threads and similar. So we're trying to tease that out of the...
it's not hard. It turns out that doing that, you typically do that through GDB init script. I mean, so you can use a GDB script that will automatically load the driver for you and then
or
pull the
particular
information. But
module that you're interested in.
yeah.
Their patch lets you examine all of the modules, treat them as if they were dynamically loaded
So
like
what
this.
they're doing is they're hooking the module init code, which is in module.c inside of the kernel. And the module init code around line 2912 or so of the module init code is the function that actually hooks the loading of drivers. And if you hook that function, then you can actually walk down through the table of all the drivers that are loaded and then pull the driver of interest.
Yeah.
So, yeah, actually, it's a modification of a script that Chris Hallinan did in his first Linux, embedded Linux primer book. So that's probably what they've done.
Yeah.
That would be my
So
guess.
They've integrated it into GDB as a proper target.
Cool.
So you can also inspect threads, break threads, that type of stuff. So yeah.
It'd be nice to be able to tease that out of them. That
Yeah.
would be really good. Yeah, it'd be nice if they would cooperate with the...
So what are you using as an OpenOCD target?
I'm using a FlySwatter 2 from Tin Can Tools and a BeagleBoard XM.
Right. I know there's support for the Snowball, but apart from that, it's very piecemeal.
Well, OpenOCD is a work in progress, and I really wish that it were better. But the fact that you can do anything with a $50 JTAG is a remarkable.
Or better than nothing.
Yeah, it's better than nothing.
Yeah.
Much better than a sharp stick in the eye.
Well, okay.
Okay. They're not. Because I do remember computers with tubes. I use computers with tubes. how dry we want to read the whole file. You don't have to, after every time the drive be bad, in which case we could see a kernel panic or a kernel oops, and in that case, by the way, kernel panics fatal to the kernel. The kernel is dead. You got to use that. A kernel oops, because you don't know what it did with the oops. This thing called BusyBox, and if you can hack normally, all right. So several different things that we potentially do. Okay, first line. Of course, very famous email. That's kind of everyone seems to hold to that. Logs, of course, the system's log and the main log will be able to capture. You can, with a static link driver, you can debug it with a JTAG. If you the boot sequence, stepping through code. Implies that if you, for whatever reason, pile into it, comfortable with the assembly language of the project, a consultant. I'm just saying, assembly language, maybe the kernel is not the place that you should be playing around. There are other techniques, however, for being able to debug trees. We have of those things, the store and retrieve calls. We have printk. We have, of course, JTAG. The JTAG piece that if you go out and Google material, you find a set of presentations from Embedded Systems Conference that get into J probes and KRET probes and system tags, F trace, O profile. So Google Mike Anderson Linux debug and you'll come up. Here we have the JTAG port. JTAG is the Joint Test Action Group, and it was a working group that was formed in order to develop a technique to test. Now, and our could have 68,000. Different thing when we see leads on what the JTAG ability to look at each one of the individual pins to not only can you do the JTAG has a lot of capability. Each one of these little things, and it would, if it board, difficult to work with today's complex boards. CPU. We can enumerate them and reach out and touch any of those devices. So, from the perspective of being able to exercise the card when somebody comes back. Poll patterns, A5, A5 type patterns. So you're looking to make sure that there's no rot happening, that you've got the refresh rates and everything turned on. So, real important capability. The JTAG itself is just a really simple protocol. And that leads to a concept of something called a Wiggler style interface. Wigglers interface. Key pieces that we have data in, test data, the clock, the mode select, the only 4-pin tag. It's nice to have this reset line. The processor. Supported by JTAG, it basically boils down to almost all processors have a JTAG interface on them, including the x86. The x86 had JTAG, wired because it turned out the JTAG connector looked remarkably and people would plug in USB peripherals into the processor and fry it. So did not to wire it out on the motherboard. That with the introduction of the Atom now has two primary JTAG interfaces. One's called an ITP700, and it's a little white plastic connector. The other is called an XDB, or an extended debug port. When we talk about JTAGs on the x86, kind of the downside that we have with the x86 at this point, excuse me, is that I can buy a simple ARM JTAG. Let's see if I can get it up high enough here. I don't know, maybe you can see that. That is a FlySwatter 2. I think it sells in a nice green plastic case. This is a beta of that board. Sells in a nice green plastic case, about $79. And it will do from a company called American Arium. 13. The argument that manufacturers, okay, that's it. BIOS manufacturers, okay, there's two. So, for the x86, we tend to have to resort to stone knives and bear skins. It's blinky lights, blinky LEDs, and things of that sort on the x86. That is changing. They're happening right now with Intel to be able to. So hopefully that will change in the not too distant future for the x86. But all the processors come with JTAGs. And for a so as a platform designer that you do have input. Design meeting and raise your hand and say, hey, make sure you wire the JTAG out. Otherwise, we're not going to be able to debug this thing. Yeah? If you're willing to give your first has been very good about providing information to the core boot project so that we can get a replacement for the evil BIOS. But unfortunately, Intel has not been quite so cooperative. So Intel is wonderfully cooperative in a lot of places with Android and Linux. Don't get me wrong. I like what they do with their video, their wireless cards and things of that sort. They've got good support there. But when it comes to the actual initialization sequence of the processors, there's still a lot of information that they hold in. And certainly, interfaces, there's a lot of special registers that if you don't have a JTAG that can capture all the bus cycles, they go, what was that? Somebody wrote to what? What is that address? That's not even on the data sheet. Oh, but you have to do that because it disables some weird the chip that if you do that, it doesn't work. Those kinds of crazy things. So yeah, hopefully Intel will start working as they try to push the Atom out as an Android platform. They will be more cooperative. And .2 spec and the 1149.7 spec both update that a little bit because it turns out that 100 megahertz is not very fast when you're to sample a 3 gigahertz processor, certainly on the x86 side. We need to have a faster interface. That being said, even the 100 megahertz is plenty fast enough for most of the work that we have to do for driver debugging. So the connection to the host typically can be a parallel port. It can be USB, Ethernet, like this one here. This is a BDI. I like the Ethernet ones. They have the advantage that the hardware doesn't have to be sitting next to me. I just have to have a network connection to the hardware. Just realize that there's now latency in the link. So if I'm debugging hardware that's located in Bangalore and I say, oh, stop, I may have missed what I was looking for by the time the message actually gets to Bangalore and actually touches the hardware. So JTAG connections, we see a lot of stuff that's being done via USB these days, and that's good. LibUSB on the Linux side works reasonably well. There are equivalents for both Windows and OS X, which we'll talk about with OpenOCD. Now, the JTAG interface itself, they may have a proprietary API, like here, this is Wind River's API. This one happens to be sitting inside of Eclipse. Alternatively, we can use some of the open source APIs like DDD in this case. When we do our JTAGs, there are basically two approaches to how JTAGs interface from a software perspective. One, they have a In some cases, they have a completely proprietary interface, proprietary software. In one particular circumstance with American Arium, one that I've worked with in the past, you actually have to have a Windows box in order to run their software to run the JTAG. And personally, I find it a little odd to have a Windows box to debug my Android platform. And I certainly don't want to have a Windows box to debug my Linux platform. That's just sacrilege. But nonetheless, some cases for proprietary interface software, you have no choice, and that's what they have. Alternatively, and this is the approach that I like to take, many manufacturers now have a GDB-style interface attached to their JTAGs. So it says that I can start up any GDB debugger, say target remote, and give it an IP address or a connection, dev TTY USB 2 or whatever, and it will connect to the device, and I can talk to it using GDB commands. This gives me a nice, convenient, familiar interface. If I want to use a GUI, I can run DDD or Insight or Eclipse or any of those front ends. But then I know exactly what the debugger does on the backside. Now, what can you do with a JTAG? Well, you can reflash with JTAGs. Obviously, you can go out and whack registers. That's an important thing, especially during the debug cycle. But it's when it gets as a debugging aid that the JTAG really comes into its own. As a debugging aid, we have to be able to describe the characteristics of the CPU and the characteristics of the board. So what has to happen is we have to get access to the register maps. We've got to get data sheets that explain which registers do what on the particular processor and on the board itself. So the way this is typically done is through a set of register files. And these register files will define things like, in this case, we have the SDRAM controller memory register. It is a 32-bit register sitting at this address in memory. So what we're going to have to do for our JTAG is, especially if we have a brand new board, we have to go through and describe to the JTAG where all the registers are, how wide the registers are they read, write, read-write registers. Sometimes we have write-only registers, which can be really interesting. And then once we've described that, then we have a pretty good map of what the board looks like. This is a really important step and cannot be skipped, because with this map, we take this exact same map and we give it to the board support package folks, and then this is used to describe the I/O map for the processor. So all the things that go up into the fixed KMAP address space, the physical address space that happens up above the kernel, all of that information, they'll be able to take it directly from this code. Also, inside of these JTAGs, they'll have processor reset sequences, kind of like macros. So we take this processor reset sequence, once we've got the SDRAM controllers working, we take that reset sequence and then we can translate that directly to assembly language code, which of course is required for the initial startup, that power on jump cycle that we have during the boot cycle. So you can't really skip this step. You have to figure out exactly how the processor is mapped, where the registers are, how the board is mapped, where its registers are, and then once you have that whole map, now you've got something that's a very substantial piece of work. This can take weeks to create this file. And management has a tendency to come around and say, what have you done for me lately? And you say, well, I've got 5 more registers described. And that doesn't sound very exciting to them. So you always make sure that you have something around that can blink an LED, especially a blue LED. They're really fascinated by blue LEDs. So when they come into your cube and say, what have you done for me lately? Well, here, watch this. And you just have it blink an LED. So an Arduino or something setting off to the side, blinking an LED, good thing to have if management stops by while you're working on these registers. So what you're really looking for, though, is you're looking for, yeah, question? Well, for instance, I have a customer right now that subbed the work out, the actual PCB design work, to a company in Germany. And that company in Germany then subbed that work out to a company in India. And the Indians are claiming that it's their proprietary knowledge, and they're not releasing the schematics. I warned them, when you sub this work out, make sure you get this, the schematics, make sure you own them, et cetera, et cetera. They didn't do that. It's something that you want to try and avoid. You would like to get the schematics. Right. That's correct. And of course, it can also be more complicated in that if you happen to be using parts from particular vendors, like, oh, I don't know, Marvell, they tend to not want to release their data sheets. Even if you're a customer, unless you're buying 100,000 parts from them, if you're buying from a distributor, they don't recognize you as a customer. So it can be very difficult to get access to data sheets. So even though you have the board, it was legally produced, and you have the schematics, you still may not be able to get all the data sheets out of it. So getting the data sheets is the process that starts long before the hardware is delivered, because it's going to take you weeks to get all that information in place so that you can then start working on these register set files, description files. Now, it's also really important when you talk to a JTAG vendor, and there are lots of them out there, talk to a JTAG vendor and ask them, is their JTAG MMU aware? Now, what that means is, does it understand the Linux kernel's use of the translation from physical to virtual space? If they don't understand how the MMU works, and they don't have that already built into their software, then basically it's an interesting paperweight that I can use to flash the flash, but I really can't use it for debugging. So make sure you ask the question, do they in fact support MMU awareness inside of their JTAG interface software? So to kind of close the loop on that, we have this project called the OpenOCD project, and it's the Open On-Chip Debug project. It was started in 2008 as a master's thesis. And it was originally designed to talk to AVR-style processors like Arduinos and things of that sort. And as they were going through this, they found that, hey, we can extend it. We can go beyond the AVR, simple 8-bit processors. We can go to ARM7. And then once they had it working for the ARM7 TDMI, they could port it to ARM9. Then they went to ARM11. Now they've got it working on the Cortex. So they keep adding to it. This is actually a SourceForge hosted project. And the one downside that I would say to OpenOCD today is that it doesn't support multi-core yet. But that's okay. That's not all is not lost, because on the command line to the Android kernel, we simply pass the no SMP option on the command line, and it shuts the other processors off. So we can then use it to debug the device driver in single core mode and then turn on the multi-core later. So the fact that it doesn't support multi-core yet is not a showstopper. It would be nice if it did. They will eventually have it, but it's not there right now. Yeah, Bill?
What about if you're trying to debug it before it gets to the point of running start kernel?
The boot firmware does exactly the same thing. It shuts off multi-core. So I've never seen a multi-core boot. It's always single core, and then the kernel turns on multi-core at the last possible moment, because there's too many things that can go wrong with multiple cores running. All right, yeah? They say that this year they should have full multi-core support for the Panda, which is kind of the existence proof on the Cortex A9. So with 060, the one that I just pulled from the Git repository last night, they claim to be pretty close on multi-core. So I suspect May, June timeframe maybe, and I'm just guessing at this point, but based on how much progress they've made over the past couple of quarters, it looks like a springtime kind of thing, I'm hoping. Oh yes, absolutely. If you've got ideas, as a matter of fact, like Android, they've now added Garrett to the repository. So now they have an official mechanism for you to submit your patches and get them reviewed using the same Garrett tool that we use in the Android community. So this is all a very positive direction for this. Now, the repository is located here, and it's a standard Git repository. We'll show you some examples of how to pull it here in just a second. OpenOCD, as a software environment, is supported on all three of the major OS platforms. So it's supported on Linux, it's supported on Windows, and it's supported on OS X, on OS X for the Mac. You'll notice that Android is not listed here, and that's simply because the user support for debuggers and things of that sort typically isn't in an Android platform image. So it's not that it couldn't potentially support Android, but then that would be Android debugging Android, and you're on the platform that you're trying to debug. That usually doesn't work too well. So normally we're going to have a development host, a Linux or Windows or an OS X development host, and then we're going to have a target that we're going to be working on, and the target is the thing that we're under control here. Here is the OS X installation. There's the Windows installation. The Windows installation then also pulls in this thing called Yagardo, which is yet another GNU ARM compiler or something or other. I don't know. It's a big, long acronym. But it then brings in the ARM tool chain. So you can use the ARM tool chain that is in the Android software development kit, or you can use this tool chain, or you can use any one of the other ARM tool chains that happen to be sitting out there. The one thing I will caution you on is GCC 4.5, 452, I think, actually 451 and 452, seems to have a problem in producing correct assembly language code for certain ARM processors like the Cortex-A9. So if you stick with GCC 4.4, that works. 4.5, a little sketchy. Maybe they'll have it fixed by 4.6. I'm cautiously optimistic. Oh, by the way, the Yagardo stuff also includes support for Eclipse. So if you really want to use OpenOCD from within the Eclipse environment, they have the Java plugins to run OpenOCD from Eclipse. Now, how do we get and install it on Linux? Well, the easy thing to do is just do a git clone and just specify the OpenOCD patch. It'll pull down the repository, cd to OpenOCD. We'll issue this command called bootstrap. The bootstrap command then looks at your system and provides additional information to configure. Configure will enable maintainer mode, and that will then allow us to rebuild the kernel. There's another option if you happen to be using the FTDI 2232H. Again, send me an email, and I'll send you all the gory details for how you do that with OpenOCD. We then do a make and a make install. This will typically install the compiler, the OpenOCD tools and support code into user local. So it'll go off into the local directories. Now, we need to enable the interface that your JTAG uses, and it turns out that OpenOCD supports over 50 different JTAG interfaces. So I happen to be using the FlySwatter. I'm actually using the FlySwatter 2, which is down there, FlySwatter, and there's a FlySwatter 2 now. But Bus Pirate is one. There are the IcePick is another one that's being used. So if you take a look, a lot of manufacturers that have USB-based JTAGs will in fact have an OpenOCD interface available for them. So if you want to use that particular JTAG with OpenOCD, they'll provide you the information that's required to make that happen. And then there's a whole bunch of supported targets. I mean, there's a bunch of them. It's an eye chart. You can't really read it from back there. But it's interesting if you CD into the OpenOCD directory, then you'll be able to take a look at what targets are supported. The one that I'm using right now is this one. It's the AMDM37X, which is the DaVinci platform that's on the BeagleBoard XM. So what can you do with OpenOCD? Well, the fact that it's free always makes people wonder, well, okay, so why am I spending $6,000 or $2,000 for a JTAG when I can get this thing for free and use a $79 JTAG interface? There's got to be something wrong with it. And, well, the something that's wrong with it is that it doesn't support multi-core yet. That's a minor thing that hopefully they'll get fixed. But in the meantime, what you can do is you can burn flash. NOR flash, NAND flash, any of those types of flashes can be burned with it. You can load and debug code in assembly language, in C code. You can work with FPGAs and do code loads to FPGAs with this thing. So other important pieces are the ability to reach out and touch registers. So you can actually use it to exercise mechanisms on the board. So being able to reach out and touch that GPIO register that caused the chip to catch fire, you could be able to do that from within OpenOCD. You wouldn't have to write any code for that. Now, how do they support this? Well, it turns out that OpenOCD uses the tool command language, Tickle, at its base. And they have a version of Tickle called GemTickle. I assume that it's somebody's initials or something. And what this does is it allows me to create macros in tool command language. And these macros can then be used to turn around and program certain characteristics or behaviors, like a memory walk pattern, a barber pole pattern in a memory test. You could implement that in Tickle. So you can extend OpenOCD to have additional features. Now, how do we start up OpenOCD? Well, we execute OpenOCD, we specify the interface, and we specify the board. Remember I talked about the fact that when we deal with JTAGs, we have to define all the registers for the CPU, and then we have to define the registers for the board itself. That's what we're doing here. We're specifying the interface, that is, we're using USB in this case, and this is where it pulls in the definitions for the CPU and the definitions for the board itself. So that's where all that work that we did up front, trying to get the data sheets and everything, actually manifests itself in OpenOCD. Now, when you run OpenOCD, it actually runs as a daemon. So it has two interfaces. At port 4444, it has a telnet interface. So we can actually telnet to the daemon. And from the daemon, we can command things like reset, halt, send it commands directly to the registers. So we can do all of that from the command line without having to have any GUI, without even having to run GDB. At port 3333, we have the GDB interface. So from within GDB, we'll start up our GDB session, and then we'll do a target remote, and we'll specify the port 3333 to be able to get access to the GDB commands. Now, from this telnet session, pretty impressive. You can dump memory, you can change memory, you can write to flash, you can do a lot of stuff from within the telnet session. So we don't even have to start GDB for much of this. It does have file I/O and things of that sort. GDB, on the other hand, we then have the ability to load the driver into GDB's symbol table, and then once we have the driver loaded into the GDB symbol table, we attach to the target and we can start doing debugging. So I'll show you how that's done here in a second. But that's all done through port 3333, and that's using the target remote command. So it would be target remote 127.0.0.1, which is where the daemon is running. It's on my local host, :3333, and I'll attach to the OCD daemon and then have control of the the JTAG interface. It does support any of the GDB front ends, so if you want to use DDD, Eclipse, SlickEdit, NemViewer, Insight, whichever one happens to strike your fancy, be my guest. But it implements a really cool feature, which is the GDB monitor command. Now, the GDB monitor command allows me to pass commands directly down to boot firmware. So I can attach to U-boot and then start sending commands to U-boot to dump memory, turn on flash, and that sort of thing. So using the monitor command, it basically says, escape this command and send it raw across the JTAG interface and talk directly to the device. So that's a very useful tool. Here's an example of using our debugger, DDD, as a front end. We specify the debugger back end, and this we're using ARM Linux GDB, and we're going to load the VM Linux image that was compiled with debugging turned on. So when we do this command, this will start up the GUI front end, it will start the GDB, this GDB back end, and load all the symbols that came out of the debug version of the kernel into memory. So if you're debugging a statically linked driver, you now have access to all the symbols in the statically linked driver. So if you're debugging static, you don't need to go any further from this point. You now have the ability to attach to the target, set your breakpoints, and start debugging. Here's the example command for the target remote, just in case people wanted to write it down, but it's, you'll be able to get these charts, I'm sure, that'll be on, on the ABS websites. Now, what happens if I have a device driver that's dynamically loaded? I don't know the addresses of the dynamically loaded driver at kernel compile time. They're not in the kernel, so I don't have access to them. So how do I go about adding those symbols to GDB? Well, it turns out that it's really not that hard to do. In order to debug a loaded module, what we need to do is we need to find out where the module was loaded into memory in the first place. And this can be done, this is typically out in the kernel. So if we cd to /sys modules, or module, excuse me, sys module. There we go. So we're in sys module. And these are all of the modules, all the drivers that were loaded. Some of them are static, some of them are dynamic. But inside of these, what we're interested in is, let's pick that one, MT9V113. I'm not sure exactly what that driver is on this board, but we'll find out soon enough. Oh, is it the camera? So we go to sys. I hate this. I really need to get the other shell here. Sys module, no. Slash, which one was it I was going to use? MT star. Let's see if it'll do that. No, it won't let me do that. All right, cd to /sys. God, I hate this. cd to /sys. I'm such a bad typist. Module. cd to MT9V113. Now, you look at this and you go, oh, that's not terribly interesting. There's nothing here. In this particular case, this was statically linked, so there really isn't anything here. That's too bad. I picked the wrong one. Yeah, there's nothing in here. But there should be the BC LS mod. Okay, so I have a couple of ones here. So OMAP LFB. First of all, we can see, just from the LS mod output, we can see the address that it's loaded at. That's an important thing. We can also get that out of /proc/modules cat. I do have BusyBox on it. I don't know why it's not showing up here. Yeah, okay, so there's the proc modules. So let me just type BusyBox. BusyBox not found. I thought I had it installed. In any case, it's a heavy sigh. It's supposed to be here. But we have the address. This is the address of the entry point of the text segment. So that's what we need to have to drive OpenOCD. So once we have the address of the text segment, and we can either get it from proc modules, we can get it from the LS mod, we can get it from the sys module name sections.txt, which is another way to get it. Once we have that, we can use the GDB add symbol file command. We do an add symbol file mydriver.o, not the .ko, but when we built the driver, it actually produced the .o version, and then it produced the kernel object version. We want the .o version that doesn't have the kernel object stuff around it. And the address that came out from proc modules. This gives me the entry point of the text segment. Once I have the entry point of the text segment, there are usually a couple of other places that we want to add debugging tools. We'll talk about them in just a second. But this assumes that the driver was loaded. What if we have a problem where it's crapping out when it's loading the driver itself? How can we debug that? Well, it turns out that if we go into module.c in the kernel source tree, and we look down, this one happens to be for a 3.2 kernel, around line 2981, we'll see a piece of code that looks like this. This is the function that actually loads modules into memory. So we can set a breakpoint here and then load the module. And when it encounters the breakpoint, we'll then be able to step through the underbar init code, the initialization code of the module. Now, realistically, if you can't get your module to even load, you've got much bigger problems on your hands. Because the only thing the module has to do is register itself with the kernel and return 0. So if you can't register it with the kernel, you've got some really serious problems on your hands. And going to this extreme to try and figure it out, you're probably in much deeper trouble than even this will help you with. But there are cases where we're having to do some initialization of tasklets, or we're having to do some initialization of some post-driver work that can get a little iffy. So this is a mechanism that we can actually go in and debug the initialization code. Tricky part about initialization code in statically linked drivers is that the underbar init declarator means you run this code once and then it's removed from memory. So you only get one shot at debugging those statically linked driver initialization codes. So that's where something like this comes into play. All right. So what other things can you do? Well, once you attach to the target, it's going to immediately break the target. That is, stop it, not break it. But it's going to stop the target. And when it stops the target, now is your opportunity to add a couple of really key breakpoints. First of all, obviously, let's say I'm trying to debug my read function out of the driver. Then I'm going to set a breakpoint on my_driver_read. Remember, I've done the add symbol file command, which loaded the driver's symbols at the appropriate location in memory. And then I'm going to do a breakpoint on my_driver_read. This is going to be a software breakpoint. We haven't talked about hardware breakpoints yet. But software breakpoint, that'll do. There are a couple of other places that we typically want to add breakpoints. One of them is sysync, panic, and the oops entry point. So I like sysync as a breakpoint because that says that from the command line, I can stop the kernel by simply typing the command sync. And by syncing the disk, it immediately stops the kernel, kicks me out to the debugger. I can then start doing other things inside of the debugger. So from the user level, I can generate a breakpoint from within even a script. That's a handy thing to be able to do. Of course, panic and oops, those are the places where you're trying to debug your hardest code. So when you hit the breakpoint, the debugger is going to drop out to the source code. You'll see it in the GDB. It'll have the instruction pointer of where that breakpoint was encountered. You can then dump memory, print variables, do all the things you would normally do with GDB. Except that now it's going through the JTAG as its interface. So despite the low cost on something like OpenOCD, and it is a Wiggler-style JTAG interface, it's not going to be horribly fast. Transfer rates typically on these types of interfaces are in the order of less than 500 kbytes per second. So if you're using it as a mechanism for flashing a couple of gigabytes worth of flash on the device, it's going to take a long time to use this type of interface. But OpenOCD has the advantage that it's cheap. So if we're simply trying to bring up new boot firmware, or we're trying to debug the kernel, driver in the kernel, this works reasonably well. If we're trying to mass program lots of Android phones, this is not the way we would typically do it. The mechanism, of course, because it is GDB aware, it knows about all the things that GDB knows about. That is, it understands the use of hardware breakpoints. Now, I mentioned this transition that we have where we're using the boot firmware, we go to the Z image, we finally go to VM Linux, the actual Android kernel, and then we're running in assembly language and we suddenly turn on the virtual memory model. Well, when we turn on the page tables inside of the kernel startup, before start_kernel, all of that code is running in physical address space. If we want to set a breakpoint in a statically linked driver, that breakpoint won't exist yet because the kernel isn't at C0 million yet. It's still in physical space. So a hardware breakpoint, which is usually a feature of the processor itself, gives me the ability to say, trust me, this address will appear in the future. And set the breakpoint so that when the address lines get strobed that show C0 million something, it hits the breakpoint in the hardware register, and then that stops the processor and then kicks me out to the debugger. So the downside of using hardware breakpoints is that there's usually only 2 or 3 of them on a processor. So we can use them to debug very special cases during the boot cycle, but we're not going to be able to use them as a general purpose debug mechanism because software breakpoints are so much easier for that. What a software breakpoint does is it literally goes out, takes the instruction at that address out, stuffs it off to the side someplace in memory, and then puts a trap, a debug trap instruction in RAM. So that when the processor encounters that and immediately kicks out of its execution mode and tries to attach to the debugger. So let me just, for yucks here, see if I can get my OpenOCD to behave itself. I did make a sacrifice to the demo gods this morning, but I'm not sure that it's going to necessarily be enough. But in any case, /OpenOCD, we're using the FlySwatter 2 on the Beagle board. And what we're doing here is we're sending it the command that says, oh, you can't see it. We're sending it the command that says reset init. So it's going to reset. Oh, that helps if I actually paste that in. There we go. All right. Now, that error thing that was passing by, that's a known bug with this particular processor. So that's a sticky bit error that resets itself eventually. All right. So you notice that the target is halted in ARM state due to debug request. Our control special purpose register here is there. There's my program counter. My MMU is disabled. Data cache is disabled. Instruction cache is enabled. So that's the debugger running. Now, let me talk to it. And we're going to go to localhost. And we're going to talk to it at port 4444. Now, if all is well, I should be able to type help. And good. Okay, I'm talking to OpenOCD at this point. I can dump the registers. Let's take a look at the registers. Those are all the registers that I have right now. They're the contents for those registers that have actually been set. I can tell it to do a reset halt, so that will reset the processor and stop it before the entry point to the boot firmware. Now, if I'm trying to debug my boot firmware, say I'm debugging U-boot or something like that, I can then load the U-boot image into my GDB session and then start setting breakpoints. And I can set breakpoints directly from this interface. So I can do a B space and set a hardware breakpoint. Now, if I am sitting here and I'm looking at Minicom, Minicom is dead at this point. What I'd like to do is do a reset and run. And with any luck, aha, U-boot is starting up. Now, as U-boot does its thing, of course, at any point in time, I could hit the interrupt button on my telnet session and have it stop. So I'm in the middle of the kernel initialization sequence. Once this finishes with the kernel initialization sequence, I should then be able to reach out and halt the processor, dump registers, and then tell it to continue, and it should get the command line back. So I'm here, so I have the command line. If I go back to my telnet session, I should be able to do a halt. Now I can dump the registers, and let's say I'm looking at the CPSR. There's the contents of the CPSR register. I can then change the contents of that register if I don't like what I'm looking at here. Of course, on the Minicom session, I'm dead at this point. Nothing happening. because the processor is halted. I can then tell it to resume, and if I made the appropriate sacrifice, it came back. All right, so at this point, I would then load GDB. I would have the driver that I've loaded. I know what its address is. I load its addresses into GDB, and I should be able to do the same sort of thing. But I am out of time. So, trust me on that, it works. I told them it worked. This is kind of a painstaking sequence of events. The thing that you have to remember about using JTAGs, hardware is built to run at a particular speed. As soon as you insert the JTAG into the scan chain, you've changed the timing a little bit. So you may find yourself in a situation where it works most of the time, but not all of the time. That's not you, that's JTAG debugging. That's just the way JTAG debugging works. So you have to be willing to understand that the environment that you're working in here is a very primitive environment. We're setting at the assembly language level in many cases. Once we load drivers, of course, then we have access to C code. But we're dealing at a very visceral level of the operating system. So if something goes wrong, chances are you just simply reset it and try it again, and it will probably work. And again, this is something that's true for all JTAGs. No matter how much you paid for them, they will in fact all exhibit these characteristics. Hardware debugging is a black art. Okay, questions? Yes?
When you mentioned the GDB-RON escape
Mm-hmm.
monitor, you have to compile the bootloader for that feature.
Yeah, well, yeah, you have to compile the bootloader for debugging, obviously, if you're going to debug in the bootloader. But if you just want to send monitor commands, you don't have to compile you don't have to compile the bootloader in any special way if you just want to be able to send commands to it. It comes in, well, it depends on the way that the configuration file was set up for the debugger. So if the configuration file for the debugger is set up correctly, then it has access, for instance, on the ARM to the DCC channel, to the serial port channel, and it can talk to it that way. So it looks just like you're typing it from the command line. You had a question? It does. Now, it supports MIPS in that OpenOCD supports MIPS. If you talk to Rusty at Tin Can Tools and say, hey, what about that MIPS support, Rusty? He's going to go, oh, I build hardware. Yeah, it supports the interface. So OpenOCD provides you access to the MIPS, but not the fly swatter itself. Fly swatter just clocks bits. Yeah. Sorry, but he's back there. Okay. Yes, if you look inside of the OpenOCD, let's see. So here I have the OpenOCD install. If I cd to board, that's a list of all the boards that it supports. Now, not all of these boards have got JTAGs wired out to nice, neat headers. Some of them, they just go out to pads on the PCB. So you have to look in the community for that particular board. Somebody has probably already hacked it, and they know exactly which pads and what connector has to be soldered into place. I've had to do that for a lot of like Cisco routers and things of that sort, where they decided not to provide me nice, neat debugging tools, but I have a soldering iron and the ability to look at pinouts to figure out where the JTAG is. Yeah, Bill?
I briefly saw on the screen the file ecos.board.c. Is that a reference to the ecos real-time operating?
Mm-hmm. Yeah, ecos, they debug a lot of ecos using OpenOCD. Yeah, back here in the back.
Sorry, quick question about the Cisco routers and stuff. When you see something that you're pretty sure looks like the JTAG header or the pins or the pinholes, what is the easiest way when you don't have the pinouts in front of you and pinouts that are you, is being especially helpful, to figure
Yeah, it's, basically you're looking at impedances on particular wires to see whether they're a transmitter or receive. You're tracing that back to the actual processor itself to see what pin you think that's coming off of the processor. And in many cases, they will have pull-ups or pull-downs that'll be soldered into place to basically disable the JTAG port. So what you have to do is find where the JTAG would have been wired out. Sometimes they'll even go so far as to actually, on the solder mask, they'll say JTAG, which is really convenient, but unfortunately not all of them do that. So if you don't have something that's that nice, basically you're just tracing through. I mean, it's a brute force kind of thing. But I have had cases where I've had to solder or unsolder surface mount resistors in order to eliminate pull-ups or pull-downs, or add pull-ups in order to reactivate the interface. And then once it's reactivated, you'll see it real fast. I mean, you'll see it start clocking data out. Yeah? They've been uploaded to the Android Builder Summit folks. So they will have a website that you should be able to log into and download all the charts. And then this is actually being recorded by the Open Electrons folks. So it'll be out on the web in probably another week or so. Not really. This requires, to debug user space applications. First of all, there is an argument for using a JTAG to debug user space applications, but that's what GDB server does. So you really don't need to use OpenOCD or any JTAG to debug user space. But let's assume that you wanted to debug user space with a JTAG. Then what has to happen is the JTAG has to support run mode. So there's two modes for a JTAG. There's halt mode, which stops everything on the processor. And then there's run mode that allows some things to keep working, but not everything. So only some JTAGs, like American Arium has one for the ARM that supports run mode debugging. And you can set a breakpoint in a user space application and then trace it all the way up into the kernel, all the way through the device driver, and all the way back down. That's a really cool thing. It costs you $6,000 to have that really cool thing, because that's how much their debugger costs. But if you need that, that's a really cool thing. And it's just money. It's only money. Any other questions? Yes?